Section 8.1, Sequences and Series. These are the objectives. You can pause to read. I'm moving on to the next slide. This is the vocabulary key concepts. You're going to see some of the concepts that you saw in Algebra 2. So you should be familiar with what you're seeing. Most of it. Next slide. It says write the first 5 terms of the sequence. Assume that n is equal to 1. So here's the rule that you're going to be working with. So the first thing we're going to do is we're going to find the first term. We're going to let n equal 1. Once we do that, whenever we see an n, we substitute 1, and this is what you get. Now you simplify this expression, and you end up with the first term being 0. Then you do the same thing for the second term. Now you let n equals 2. Substitute n. For n, substitute 2. You simplify, and you get the following: 1/2. So this is your second term. Third term of the sequence is going to be the following after you simplify, which is 0 again. The fourth term, once you simplify this, you get 2/8, but we can simplify that, put it in lowest terms, and you get 1/4. The fifth term of the sequence becomes 0, and these are the first 5 terms of this sequence. Let's look at number 2. The rule is slightly different, but we apply the same steps. To find the first term, we let n equal 1, and then we simplify 3/4. To find the second term, we let n equal 2. You get 9/16. By this point, you should follow. This is 27/64 for the third term. For the fourth term is 81/256. The fifth term is 243/1024. So here are your first 5 terms of number 2. Let's move on to the next slide. It says use a table of a graphing utility to find the first 10 terms of the sequence. So this is the rule that you're going to be working with. A sub n equals 4n squared over n plus 2. What I'm going to ask you to do is just copy this table, and then in class I'll clarify to you how you can use the graphing utility to generate all these numbers. You might be able to figure this out on your own, but just in case, like I said, I am going to show you how to do this in class. Let's move on to the next slide. Now this one is basically going to be the opposite of number 1 and 2. Number 1, I give you the rule, and I ask you for the first 5 terms. Here, like I said, you're going to do the opposite. I give you the terms of the sequence, and you tell me the rule. Let me read the directions. It says write an equation for the apparent nth term of the sequence. Assume that n is equal to 1. And like I mentioned at the beginning of this video, you did this in Algebra 1, and Algebra 2. So first notice that to go from 3 to 7, you need to add 4. From the first term to the second term, you add 4. From the second term to the third, 4, and you get the point. Which means that your rule is going to have the following. A sub n equals 4 times n. If this was, you keep adding 2, this will be 2 times n. If this was, you keep adding 7, this will be 7n. But notice that this does not really generate the first term of 3. So if you apply the rule and you let n equal 1, notice that becomes 4. But the first term is not 4, it's actually 3. So how can we make this first term into a 3 if it's a 4? All we need to do is take away 1, which means that your rule is going to be the following. And notice that if you apply the rule, let n equal 1, 2, 3, and 4, you're generating these numbers in this sequence. Let's look at number 5. So at this point, you notice the same as number 4. If you look at the denominators, you keep adding 2. If you look at the numerators, you keep adding 1. So now, your rule is going to have something like this. 1 times n in the numerator and 2 times n in the denominator. Now, if you let n equal 1, is it going to generate the first term of this sequence? The answer is no. You get 1/2. We have 2 over 1. So how can we make this 1/2 into 2 over 1? We just need to add 1 to the numerator and subtract 1 from the denominator. So that's why we have the following. And you can make this prettier. And this will be your rule. Let's look at number 6. So now, notice that you don't keep adding the same number in the numerator nor the denominator. Basically what you're doing, in the numerator you keep multiplying by 2. In the denominator you keep multiplying by 3. So that means that your rule is going to have the following. This is the base, is being raised to a power. Why to the negative 1 though? Well, it'll make sense in just a little bit. And 3 to some power, to the n power. Now, if you let it equal 1, notice that you get 3 for the first denominator. If you let it equal 2, you get 9 for the second denominator, and so forth. So this matches. Now, why do we have n to the negative 1? I mean, n minus 1 as a power? Because if you if you just let the power be equal to n, you're not going to be generating 2 as a first number. You're going to be generating 2 as a first number, and we don't have 2, we have 1. So that's why if we take away 1 from the power, you generate these numbers. 1 when you let n equal 1 for the first numerator. When you let n equal 2, notice that it becomes 2 minus 1, which is 1. 2 to the first power is 2, and so forth. Now, this does not take care of the sign. Notice that you have positive, negative, and this is how you take care of the sign. You work with negative 1 and you raise it to a power, and you want to raise it to the n plus 1 power because you want the first sign to be positive. Now, I can clarify this a little bit more in class. Just talk to me. But you can express the rule for number 6 the following way. Why? Because it just, excuse me, it's the same answer, but this just looks prettier. Okay? Let's move on to the next slide. This is what we call a recursive sequence. Let me read the directions. Let's write the first 5 terms of the sequence defined recursively. Notice that you have a sub 1, which is equal to 15, and then you have this. So let's find the first 5 terms. The first term is actually given to us. A sub 1 is 15. So let's find the second term. To find the second term, we're going to have to let k equal 1. If k is equal to 1, notice that you have a sub 2. If you let it k equal 1, now this becomes a sub 1. And then you still have plus 3. Now, how do we find a sub 2? A sub 2 is whatever a sub 1 is plus 3. A sub 1 we found out it was given to us, that was 15. That's why a sub 2 is 18. Let's find a sub 3. To find a sub 3, we need to let k equal 2. Once we substitute k equals 2, notice that it becomes 3. This is just a sub 2. And we get the following. I know that a sub 2 is equal to 18. Substitute. And that's how I get 21 for a sub 3. A sub 4, we're going to have to let k equal to 3. We substitute into the original rule. I know that a sub 3 is 21. And this is what I get for a sub 4. At this point, you should see how we get a sub 5. And again, I can clarify this in class. These are your first five terms of this sequence. Excuse me. Here's number 8. Now, here I give you a sub 0, a sub 1. And this is the rule. You have to take this k into account. The k has to be greater or equal to 2. So now, the first term is given to us, which is right here. Now let's find a sub 2. To find a sub 2, I just basically need to let k equal 2. Then I substitute k equals 2 here, and I get the following. Now, what is a sub 0? A sub 0 is 1. What is a sub 1? It was also given to us, which is 1. So that's why a sub 2 is 2. Let's find a sub 3. So to find a sub 3, I need to let k equals 3. I substitute k equals 3 here. I get the following expression. Then I know that a sub 1 is equal to 1. A sub 2 is equal to 2. I substitute, and a sub 3 is 3. A sub 4. We let k equal 4. Substitute in here. I get the following. I know a sub 2. I know a sub 3. And that's how we end up with 5. The last term in this recursive sequence is 8. And again, you should follow. This is actually a very famous sequence. If you ask me in class, I'll give you the name of the sequence and also why is it so famous. Let's move on to the next slide. This is where we have to use the factorial notation. This exclamation symbol is what we call factorial. You saw this in Algebra 2. So here we go. Let's simplify this. This, you should remember that 10 factorial is the same thing as 10 times 9 times 8 times 7 times 6. And we can keep going times 5 times 4 all the way to 1. Now, why am I stopping here at 6 factorial? Because in the denominator I have 6 factorial. And these actually cancel out. Now, 3 factorial I leave alone. Why do I leave it alone here? Because I have 4 factorial in the denominator, and I can just rewrite this as 4 times 3 factorial. So these two are going to cancel out along with the 6 factorials. So once I cancel the 6 factorials and the 3 factorials, I'm left with whatever this is divided by 4, and this is my answer. Let's look at number 10. Number 10 is just like number 9, but now we have variables in the expression. Now this is just n plus 2 factorial, and then this is n factorial. Now you should agree with me that the numerator is larger than the denominator. Why? Because this is 2 more than the denominator. So what I'm going to do, I'm going to basically apply the same idea we applied on 9. I'm going to work with the larger factorial, and I'm going to keep breaking it apart. And notice that I'm going to have, I ended up with 10 times 9 times 8 times 7, and I stopped at the 6 factorial because I know it's going to cancel. So then I'm going to do this. I'm going to write the following expression. N plus 2. Why do I write n plus 1? Because it's 1 less than n plus 2. Why do I write n after n plus 1 because it's 1 less than n plus 1. And at this point, I notice that n factorial and n factorial, these cancel out. If you need me to clarify why I have n plus 1 after n plus 2, I can do so. But like I said, how do you get 9 from 10? You basically take away 1 from 10, and that's how you get 9. So I am applying the rule for factorials. I have this first factor. How do I generate the next factor? I take away 1. I take away 1 from 2, and I get n plus 1. So the final answer for number 10 is the following. You don't have to FOIL or multiply this to binomials. Let's move on to number 11. You did this in Algebra 2. So 2 parts, you need to find the fourth partial sum. Second part, you need to find the sum of the infinite series. So the first part, basically all we need to do is fourth partial sum means that you need to start with the lower limit and end up at the fourth term, the upper limit of 4. So you need to add the first 4 terms in this summation notation expression. So then, and notice that this is what we call a series. When you start adding the terms, we call that a series. If we just list the numbers, we call that a sequence. So anyway, so now how do you should know how we generate this. Quick review. Notice that this 4 is I just treat it as a factor. How do I get 1/10? I just basically let k equal 1, and I get 1/10. How do I get 100? I let k equal 2, and I get 1 over. I get 1/10 squared, which is 1 over 100. This is k equals 3. This is k equals 4. And then at this point, all I need to do is I need to add all these numbers, multiply by 4, and I get the following. This is part A, or part 1. Part 2 is basically to find the sum. If you were to keep going all the way to infinity, and you learn how to do this in Algebra 2. This is the formula you saw in Algebra 2. This is what we call an infinite geometric series, and the infinite geometric sum, when it converges, is when R is satisfied by this inequality. So in this case, the R, or what you learn in Algebra 2, is what we call the common ratio. This is your common ratio 1/10. Since the common ratio is satisfied in this inequality, the absolute value 1/10 is 1/10. Is 1/10 less than 1? The answer is yes. That's why this is the sum of this infinite geometric series. So for a sub 1 is basically the first term. What is the first term? 1/10 times 4. And then 1 minus 1 over 10, because this is your common ratio. You simplify this and you end up with 4/9. And like I said, you did this in Algebra 2, and if you want me to clarify this even further in class, just talk to me. Let's do the last one. Same directions, different problem. So the first part, you have the following. This is when I is equal to 1, when I equals 2, I equals 3, and so forth. And you end up with this sum. And for second part, you have to apply the formula that you learned in Algebra 2. Is this going to generate a sum? Is it going to converge? And the answer is yes. Why? Because the absolute value of 1/5 is less than 1. So what is the first term of this series? Is 2 over 5. That's why you see that here. The common ratio is just 1/5. You simplify the following, you end up with 1/2. I didn't say this on number 11. I'll say it quickly. But notice that these two numbers, if you were to punch this into the calculator, you're going to get something very close to this number. The same thing on number 11. Part 1, if you come up with a decimal, should be very close to what we ended up with in part 2. This concludes the video.